here, actually not units of pressure, but a unit about pressure. And I'm going to go through every state of matter. So in chapter 18, we're going to begin with solids, and then we'll go into liquids and gases in chapters 19 and 20. But if you turn to page 345, that's page 345. If you're dyslexic, that's page 543. Yeah, 543. We're going to first of all talk about how most solids have some sort of crystalline structure. And if you're looking at the picture up here, you'll see that there is a common substance that you eat every day called table salt. And in this table salt is a combination of many molecules of sodium chloride. The sodium chloride is naturally made up of atoms of sodium, which in this case are going to be looking green, or looking white, and then you have the bigger chlorine atoms, which look green. And if you notice, sodium wants to get an electron, chlorine wants to give one away, so there's always a green and a white that are matched together, and as they share that electron. But the way we can tell what a substance is first of all through its density, and that's why Molecule Man showed up to sing to you, because all the different elements have different densities. We can also look at specific heats. But one of the more complex ways they do is they take X-rays and they'll shine it onto the elements. So if you look in the left-hand picture that you see over here, you can see an X-ray coming down through there. And X-rays are small enough to go through the spaces between the atoms. Well, just like when you take an X-ray at the doctor's office, if it hits a bone, the bone shows up white on the X-ray. Well, when you take a picture X-ray of a crystal, when the X-ray hits one of the atoms, it will show up as white on the X-ray. And so if I scroll down here, you're going to see an X-ray picture of a sodium chloride crystal, and you'll see that the great big white dots are where it hits the chlorine atoms, and the smaller ones are going to be the sodium atoms. And I think it's the movement of the electrons around that causes the other diffraction patterns that you see there. In other words, or it could be that the X-rays are just hitting those atoms and diffracting. But every different element or every different molecule is going to have a different crystal X-ray pattern. And so you can actually take pictures of it. And that's the answers to the first couple questions on tonight's homework. Now, we talked about density on page 346. We did that already. I do want you to know, though, that density is often also called specific gravity. So don't get that confused. The next thing we talked about on page 348, and it's not this picture here yet, but is the Hooke's Law. If you remember in Hooke's Law, we put weights on different springs, and what the Hooke's Law constant, or the spring constant, told you was, let's say if you put 20 grams on the spring and it stretched 10 centimeters, well then 40 grams would stretch 20 centimeters, 60 grams would stretch 30 centimeters, and so forth. So it's how much does it stretch for every amount of weight you put on it. That's what the spring constant is. Well, you got to remember that force is directly proportional to stretch. And one of the questions on the homework says if you double the length of the spring, well, that means the spring is going to stretch twice as much. If you would cut the spring in half, that means the spring is only going to stretch about half as much. Okay, so eventually that spring, though, is not going to bounce back, and this is what we call the elastic limit. And that's where we want to start talking about right now. If you want to become an architect or a engineer, this next picture here is something you got to really pay close attention to. So on this picture, you see a beam that has a weight on the right-hand side. And if I were to ask you where the most stress is on this beam, would it be on the top, would it be in the middle, or would it be on the bottom? Well, if you notice, the top part of the beam gets stretched out because the wall's wanting to pull it to the left, the block's wanting to pull it to the right. The bottom part of the beam gets compressed in, so it has some stress on it. But the middle part of the beam hardly has any stress on it whatsoever. So to make things roughly cheap, what we do is we change the shape of the object. Let me show you what it looks like. So if you look on page 351, you'll notice that when they make skyscrapers and very, very large buildings, they use a beam that's in the shape of an eye. So it's strongest on top, it's strongest on the bottom where the compression and the stretch actually happens, but the middle part they make very, very light. And that way it doesn't have to lift as much weight. It's a lot cheaper because you don't have as much metal. And once again, it's just as strong because all the strength comes from the top and the bottom. Now, some of the strongest shapes are triangles, and if you look at this bridge right here, you can see all the different triangles that you see in the bridge, but every triangle brings the weight down to the support base. So you can see that the girder that actually puts it into the river or the lake or whatever it's in, these triangles are forcing the weight of that road back to that girder. So triangles are very, very, very strong shape. Actually, the strongest shape, though, is this one right here. It's called a catenary. And here you have Cody Coleman or Brady actually holding up the St. Louis Arch. And if you look at this arch, all the weight gets transferred down to the base. And there's also a keystone up here in the middle that when the left-hand side wants to go to the right and the right-hand side wants to lean to the left, that capstone is also compressed and holding up the weight. So actually a dome or a catenary like this is actually your strongest shape. Let's see here. I thought there was one more thing I needed to go to. Go to the next page. There we go. I think I'm still recording. Okay, good. The next thing I want you to try to do is if you have an egg, we're going to actually try to do this. I'm going to get Wyatt here to try to crush an egg with his hand. And since an egg is in the same shape as an arch, he can squeeze that egg as hard as you possibly can, but he will not be able to break it. Now, when you do this, whatever you do, don't push in with your fingertips or you will crack the egg. So you're cradling the egg between your two middle fingers and the palm of your hand and squeezing as hard as you can. Right, the last thing I want to talk about is what determines strength in physics. And it's actually a ratio of two things. It's the ratio of the surface area divided by the volume. So I want you to look at some of these cubes that I have in this picture here. If you notice, here's a 1 by 1 cube, and so its area would be 1. Now, I admit you have to multiply that by 6 because there's 6 sides. So 1, there's 1 for each side, and there's a top and a bottom. So it would actually have a 6 square centimeter surface area, but just the cross-sectional area is going to be 1. Its volume is also going to be 1 because it's base times height times length, and so 1 times 1 times 1. Now, let's double that. If I double it, if you notice the surface area goes from 2 times 2, which is 4, so I went from 1 to 4, but watch what happens to the volume. It's now 2 times 2, which is 4, times 2 again, which is 8. So I went from 1 to 8. So if you notice, the volume grows much faster than the cross-section area. Same thing happens with you go to the block with 3 going across. So the area would be 3 times 3, which would be 9. So I went from 1 to 9. But the volume is going to go 3 times 3 times 3, which would be 27. So I went from 1 to 27. So the volume is always growing much, much faster than the cross-section area. Well, the way you determine the strength is by taking the ratio of it. Now, the ratio of the surface area to the volume. So on that first one, if you remember, one block had a surface area of 1, but you had 6 blocks. I'm sorry, 6 sides rather. So I'm going to take the surface area of 6 and divide it by the volume of 1. So it would have a strength of 1. Now, I then doubled that block size. And when I doubled that block size, it went from 2 times 2, which is 4, and I don't know where the picture of this one is. Let's do the one where I tripled it. No, here it is right here. It's doubled right here. So therefore, I'm going to have 2 times 2, which is 4. You have 6 sides, and so 4 times 6 gives you 24. But its volume is 2 times 2 times 2, which is 8. So watch what has happened there. 24 divided by 8 is 3. So if you notice, the surface area to volume ratio went from 6 up here down to 3. So in physics, we consider that smaller block stronger. So let's just pretend you were making this block out of straws, okay? And there's no water in it. There's nothing solid about it whatsoever. These small blocks would be much stronger than the block that was twice the size, okay? Because the straws would want to bend. If you look over here at the next bigger block, now I have sides that are 3 centimeters long. So the area is 3 times 3, which is 9, but I have 6 sides. So 6 times 9 gives you 54 for the area. Its volume is 3 times 3 times 3, which is 27. So 54 divided by 27 is only 2. So I went from having a strength of 6, what we call the surface area to volume ratio of 6, down to a surface area volume to ratio of 2. And this is why in physics we consider an ant to be stronger than an elephant. Naturally, an elephant can lift more than an ant, but an ant might be able to lift 100 times its body weight, where an elephant can't even lift its body weight. So when you look at strength, surface area to volume, that's what you have to sort of look at. And so since an ant has quite a bit of surface area and very little volume, it's got a lot of strength to it. If you just want to look at an elephant, talk about some other animals here. This is an African elephant, because you can see its ears look like the continent of Africa. And it lives in a little bit hotter climate than the Asian elephant does. The Asian elephant's ears are much smaller. They look like Asia. And the way an elephant cools itself, you got to think about last chapter. It'll take some water in its trunk, throw it on its back, and it starts flapping its ears. Now, when it flaps its ears, it creates evaporation. Evaporation is a cooling process, and therefore it cools the elephant. The other thing that an elephant's ears have in it is a lot of blood. So therefore, when an elephant gets hot, it fills those ears up with a lot of blood, starts flapping those ears, and then it cools it down. The cooler the blood gets sent back to the rest of the body, and it cools it down. Which again, Asian elephants don't have to cool themselves as much, so their ears are smaller. Two last things that the book talks about. As far as cells, when cells get in a certain size, they have to divide. They get rid of their waste through exocytosis, making vacuoles escape. And if you notice, volume was getting bigger than surface area. So if the cell gets too big, it doesn't have enough surface area to get rid of the waste, and the cell stops working. And that's the problem with cancer cells. They're either too big or they're too little to do their function. Lastly but not leastly, we have the cute little fact that you might want to know, that most warm-blooded animals have a certain number of heartbeats throughout their whole life, about 800 million. And so we say that little animals will live fast and die fast. And that's because their heart beats so quick. Hearts are really small, so they have to pump little teeny blood really fast. And so they tend to use up all 800 million heartbeats, and they die relatively quickly. Where a larger animal has a bigger heart, so it has fewer number of heartbeats, so it lives longer. If you look at humans, they have probably about twice that many. So I'm thinking, well, why the heck would it ever be good for me to go out and exercise? I'm going to waste all my heartbeats that I have throughout my life. The good part about exercise is this: it makes your heart stronger, so it pumps more blood. It also makes your veins usually a little bit bigger, so there's not as much pressure, and they can get more blood to your tissues. And so when you're at rest, which is most of the time, your heart pumps a lot slower, and so you got all those leftover heart beats to take care of before you die. So if you exercise, you're going to live a little bit longer. So make sure you get all the homework done from chapter 18, and see you soon. Hope you enjoyed the show. Love you. Bye.